English or Korean? English, okay. All right, well, thanks for the invitation. It was a pretty last-minute invitation, I don't know if you know. So I'm going to just go through some of the slide deck I prepared a couple of years ago. But before I start, let me introduce myself. So I'm Kyung-hyun. I'm a professor of the Computer Science and Data Science at New York University. I'm jointly appointed at the Korean Institute of Mathematical Sciences and also the Center for Data Science at NYU. I've been at NYU about 9 years and counting, so 10 years, and was fortunate to see a lot of things that have gone really, really well in terms of the AI development. And doing so, I was fortunate enough to find the great collaborators who I was able to co-found a company together with early 2021, and I sold a company called Oppression Design to Genentech, and then I'm now part of the Genentech, which is a company within Roche, working on the antibody design as well using artificial intelligence. But today, I thought I was going to talk about something that are not really that great about the current paradigm of the AI, instead of talking about what works really well, because everyone knows what works really, really well. And then that is the reason why the title is Unreasonably Shallow Deep Learning. And in fact, what I wanted, and I'm not sure if it's possible in this kind of a stage, is to make it as interactive as possible. So if you have any questions or any comments, please do raise your hand. I'm pretty sure the organizers do have some of the microphones around, and then you can just raise your voice up so that I can actually have a chat with you as well. Before I begin, can I actually do a very quick survey? Okay, so who among you are startup founders or the work at a startup that is early enough, as in it was founded within the past, let's say, 3 years? Raise your hand. Is there anyone who is okay, I see a couple there. All right, so I heard that it was going to be all startup founders, but apparently that's not the case. All right, but that's okay. Who among you actually uses so-called AI? You know, that could be just using ChatGPT daily, or using any other technologies at your company for the image processing or whatnot. So can you raise your hand if you use AI, let's say daily or weekly or whatnot? Okay. All right, this is great. This is great. Because it's actually really amazing how things work. So I've been working on this technique called, or the group of the techniques called deep learning that are actually at the foundations of the modern AI ever since 2009 nonstop. And how much progress we were able to see in terms of how amazing things they can do in reality has been just mind-boggling. However, a lot of the technologies that we are using these days in AI have a severe set of limitations that we actually don't know how to solve at all at the moment. I'm going to go through 3 such things. Is someone, let's say, technical and less technical? I'm going to actually skip over the many of the technical aspects, but the point I want to make is that there is an issue of the non-identifiability. That is that every time you train a model or use a model that others have trained, you are going to have some kind of uncertainty in terms of how those models are going to work. Say you're using the Llama 3 for building some kind of chatbot. And then next month, you're going to get a Llama 3.1, and you decided to upgrade it by using Llama 3.1. That doesn't necessarily mean that all the things that were working well are going to continue to work well. Some of the things that were working well may actually not work well, because we actually have this issue of the so-called non-identifiability. And then second one I'm going to touch upon is so-called the spurious correlations. Unlike us, who we believe at least, are performing a causal reasoning in order to solve a lot of problems, these machine learning algorithms tend to be, or in fact, fully rely on the so-called correlations. That is what kind of things appear together with each other. It's like the example of the umbrella versus, let's say, rain kind of thing. I'll go to that one. And then last one I want to talk to you about is because some of you are startup founders or working at companies that actually have products that have been deployed, what happens if once you deploy the system? Once you deploy the system, you're actually changing how the world works directly. And then what that means is that all the systems that you have built, in particular that rely on the data that was collected from the past, will not be valid anymore from there on. So let's dive deep into each one of these topics. So first thing is the non-identifiability in deep learning. And in fact, it's a figure from the 2020, so it's 5 years old. it's not really too far into the past, but I think in AI world, it's considered extremely, extremely old. However, the funny thing that people already noticed in 2020 or even before 2014 and so on is that all these models or the systems that we build, AI systems that we build that are supposed to be perfect are somewhat weird. They don't really work as we want them to work. For instance, if you look at the third column in this slide, that is a system that was trained to recognize pneumonia from the X-ray of the chest. And then what do we expect any system or a doctor who's looking at the pneumonia, looking for pneumonia? We want them to look at the chest, actual lung. But these systems don't necessarily look at where the lung is, and then somehow makes this, accurate, let's say, prediction. So what is going wrong there? And it turned out that sorry about that. I think sorry. So it turned out that it's actually very easy for us to have a thought experiment. Let's say I want to build a bird detector. Let's say I'm a lover of birds, so I want to go for the bird watching, but it's really, really boring to do bird watching because the birds don't necessarily show up when I want them to show up. So what I wanted was to build a convolutional neural network or the VIT or whatever is popular these days to build a system that's going to look at an image and then trying to detect whether there's a bird or not. Now, let's say I wanted to build the training examples myself. I went to the Google image search. I searched for birds, and I see all those pictures of the birds. Let's say those were the 4 examples I showed you as the examples of the images in which the birds appear. And then what you notice is that based on these 4 examples, you can have actually many different ways by which you can tell whether there's a bird or not. Now, of course, you can look at the beaks of the birds. If there is a beak in the picture, there's likely a bird. Good. If there is a very beautiful feather, likely there is a bird. But the funny thing is that looking at these 4 images, what you see is that if there is a branch of a tree near the bottom half of the picture, there's a bird. Because as you can see, almost all the birds that you're going to see, or the pictures you're going to see from the Google image search, will have branches, tree branches in the picture. What that actually means is that there is ambiguity, and then this is nothing to do with what people often call technically as an overfitting. That is that these classifiers or the AI systems that you build are going to just overfit to the training examples you make. This is not the phenomenon of overfitting at all. In fact, if you build a branch detector as if it's a bird detector, it's going to work amazingly well. In fact, it's going to work well on the images of the birds that were taken from the 20 years in the past, as well as the 20 years into the future, as well as the 20 miles from here and 20,000 miles from here as well. So we can have the 2 very well-working solutions, but it's pretty clear we want only one of these solutions. We don't want the AI system that's going to detect whether there is a branch and then say that there must be a bird. But what we want is that we want our AI system to see that there is a beak of a bird, and thereby there must be a bird. So there is one solution that's better, the other solution that is not better. Okay. And in fact, it turned out that the bird detection algorithm that I just told you about that is very unrealistic, of course it's just a thought experiment, is not a hypothetical experiment. Now, let's take as an example another paper from 2019. Again, pretty old, but the lesson actually has maintained very, very well as it was back then. Smile detection. So what do we expect our smile detector to tell us? Looks at the image of the face, or the face in the image, and then probably looking around the, let's say, mouth area, lips, as well as the eyes, and then trying to tell us whether the person is smiling or not. And in fact, a lot of people are now using the face recognition, and in fact using the face recognition in order to detect the emotion and then trying to build a system that's going to react to it appropriately. But then what Denton et al. Found out was that in fact, that's not exactly what these so-called smile detectors do. Smile detectors are in fact going to look at all those different features and then trying to figure out what are the features that are going to correlate well with smiling labels. For instance, according to a smile detector that you built, AI smile detector, essentially the younger people tend to smile more. But that's absolutely not true. That doesn't mean that the older, because the person is older, our system is going to say that, well, that person must not be smiling. I mean, to be strict, on average, that may be true. However, what we are building is the AI detector that is not working on average, but working for each and every case separately. And this happens over and over. Let's say you build an amazing image recognition system, object recognition system, and then if you test the accuracy of the object detection on the images that were collected from the different countries, then you start seeing a weird patterns. One of the major patterns that was found by the DeVries et al. In 2019 was that the accuracy of this object recognition system, AI-based systems, was higher on the images that were taken from countries that have a higher income. That's really weird. Why would our classifier work better if the country in which the pictures were taken had a higher income? That's in fact because how the training data was created. The training data, which often starts from the so-called ImageNet database that was built in 2009, and then you have a lot of images that have been mined from the internet, are mostly the images taken from these kind of high-income countries. And also, income is just one thing. It's not only just income. In fact, it's going to work better in, for instance, in US than in here in Korea, just because the amount of the images that we're going to see, and then the companies that provide us services, thereby collecting the data, are mostly in Silicon Valley, as well as the various parts of the US. And then again, this is not what we think our AI system should do or would do. This is in fact the opposite of what we anticipated. And often when you bring this up, people are going to say that it's just data. It's often that's their defense. And then all we need to do is collect more data. But it turned out that it's not only about data itself. The algorithms do have a very theoretically valid reason why they're going to result in these kind of, let's say, models that have weird behaviors. Let's just call it weird for now. And then this clicker also has a bit of a weird behavior. But then the reason is actually quite straightforward. Let's say we're going to consider all possible decision rules. And then what is a decision rule? Each and every decision rule can be an AI system you're going to build that is making a decision whether the person is smiling or not, whether this sentence should be translated into this translation rather than that translation, trying to see whether there's a bird or not. So these are all decisions that are being made by these classifiers. If I think about all of the decision rules, there is only a small subset of the decision rules that this kind of AI algorithms can capture. And then among those rules, very small subset of the rules are actually the ones that we think are good because we collected some so-called test examples and then test these models on. However, among them, it turned out, as we have seen today, that we have so many different decision rules, some of which we like, but most of the others that we actually are not sure about or we want to avoid implementing at all. And then, in fact, we have known this kind of phenomenon from many years ago. This is one of my favorite papers from the 2018 from the Stony Brook. And then it's really easy to see. So what you see as a standard on the right-hand side plot is the accuracy on the test examples that they have collected, or the collected using a usual way of collecting the test set. And then they train so many classifiers or the AI systems on the training set. And then all those different AI systems work perfectly. Or they look seemingly to work perfectly. However, when they create new types of the test sets, so test sets where people are older, for instance, test sets where the sentences are shorter, or test sets where the birds are not from the forest, but from the, let's say, cages indoors, then what you see is that every single AI systems that looked exactly the same to us according to the accuracy metric that we are using are in fact very different from each other. And then again, some people are going to tell you or tell me sometimes that it's all about the matter of collecting more data and then training a model longer and longer. That's absolutely not true. Our theory and then in fact, the algorithmic insights as well as the theory tells us that that's not the case. So why does that happen? And then I don't know if you have heard of this, but there is something called a non-convex problem in machine learning. That is that how do we train these models? We train these models by optimizing or minimizing particular loss function or maximizing the accuracy. Now you can almost imagine that how you're going to teach your kids or the student is to give them the exam, they make mistake, then you're going to tell them how to fix it little by little, give them the next exam, And then the goal is to always ensure that the student's average accuracy, so that is the score goes up and up. But it turned out that in order to increase the average accuracy, there are many different ways to do so. There's not just a one perfect way to solve the problem, and it turned out that there are many different ways to solve the problem. Okay, let's see. Yes. And then this can be drawn as this kind of, let's say, figure where you can imagine that the x-axis corresponds to different, let's say, AI systems that result from being trained on the exactly same training set. And the y-axis is going to be accuracy. And then we always find many different, let's say, solutions. It's very easy to show this. In fact, you can check this by training these models very easily these days. You can go to, let's say, Lightning Studio. You can just start up the GPU instance for free. You can train these models and then see that every time you train these models, you're going to end up with a similarly good models according to your accuracy metrics, but they are all very, very different from each other. And then, of course, the Bayesian machine learning is where the people start claiming that, well, then all we need to do is collect all of them, just average it. Why not? And then this is what you hear these days from these LLM agents people or the LLM debate people or whatnot, is that well, if one LLM has an issue, we're going to use multiple LLMs. If ChatGPT has an issue, I'm going to also use the Claude and then see if which one is better. Unfortunately, the space of all these decision rules is infinitely large. There's no way actually we can cover all possible, let's say, such solutions or the diversity in the solutions. Okay. Sorry about that. Okay, yes. And what this actually says is that what is really difficult about building AI systems is not learning about how to build these AI systems, not learning what are the mathematical theories behind this AI system, not learning what is the best stack of softwares to deploy these systems. In fact, the most important and the first question you have to always ask is, how do we know that our AI systems actually work? How do we know that how well they work? How do we know that how they are solving these problems so well? And it turned out that it's extremely, extremely difficult. Of course, we want to start by saying that, okay, these days people call it vibe check, right? So you want to try it out a bit and then be impressed and then say that, oh, my AI system is amazing. And then you're going to, of course, see that, okay, is the AI system work on some of the test instances I have created? And then you want to actually ask whether this AI system is going to work well on this kind of examples that are going to be similar to the ones that the system is going to encounter in the test time or in the deployment time, and on and on and on. But as you can imagine, this example spaces is, again, infinitely large, and then the world changes little by little. So how do you know that this AI system is going to work as you anticipated on all those instances that these systems are going to be, let's say, tested with in the test time? And then this actually leads to the question of whether the observational data alone is enough. And then this is really interesting, and then it goes into a bit of a causality versus correlation. You may have already heard about the statement or the claim saying that the correlation doesn't imply causation. That's absolutely true. And then that's the example I was trying to get to, is that say you look outside on the street from your house, and then what you notice is that every day, whenever there's a rain, there are people who are wearing umbrellas. And then at some point, you start to get suspicious about, okay, maybe rain causes people to wear umbrellas, but then why wouldn't you be suspicious about the other way around? Is that what if it's actually the people wearing umbrellas that cause rain? Now you all kind of left at that's ridiculous. That is indeed ridiculous. But that's exactly how the shamans in the traditional times were claiming that how their rituals are going to lead to the rain. And then if you are born in that kind of time, and then so that every time there's a rain, there's a shaman outside their house, then you'd in fact be confused that it's actually the shaman's ritual that causes rain. And when in fact there was a confounder, that is, the shamans were just extremely, extremely good scientists back then. So being able to predict that it was going to rain, thereby they're going to start the ritual just in the right time. And then that is what we call the unobserved confounding factors. That is Z on this slide deck. And then this unobserved confounder creates so-called backdoor path. So what would be an example here? Oops. the example in the case of the bird detector was that almost always when we take a bird's pictures, we don't want to take a bird picture indoors. We go out there and then take a picture of those birds. Now, how often can you take a flying birds well enough zoomed in? Very difficult. They are very fast. So most of the pictures of the birds are birds that live somewhat in a forest or the park that are sitting on a branch. And thereby, every time you take a picture, you do see that the birds are always, the fact that there is a bird correlates very well with the branch. And then there is a backdoor path that is created via this z variable that is an unobserved confounder. And the unfortunate thing is that we cannot really get rid of this fact if we only have the observations. Unless you go out there and then decided never to use the umbrella, how would you actually know that the umbrellas don't cause rain? So what that means is that simply observing others is often impossible to break this kind of so-called spurious correlations. And most of the systems you imagine using, you have used, because most of you have been using, are completely susceptible to this kind of spurious correlations. It's pretty much impossible unless you start running some experiments with these systems directly. So what do people do? It turned out that the OpenAI, Anthropic, Naver, Hyperclova, and all those companies have been running experiments with you all in the loop. So only way we know how to break it at the moment is to run the experiments, go out there, trying to open the umbrella in a sunny day. And then if the rain doesn't fall, then you know that the umbrella is not causing the rain. But then you have to, of course, how do you do that at the mass level? Is that you deploy it and then let users like all of you, including myself, use it. And then that's what we often refer to as a human end model in the loop. And every time you use the, let's say, ChatGPT or Claude or whatnot, what you're going to do is that you're going to often slightly alter the questions until the point at which you get the desirable answer. Or ChatGPT is going to show you that, well, there are two potential answers. Which one would you choose? Or sometimes you're going to go back to your original question and then try to rephrase it and then rerun the whole thing. And that's the data that you're actually providing to all these providers in order to break these spurious correlations that cannot be broken unless somebody run the experiments. And then running the experiments implies that we need to get the new feedback, and then it turned out that we are the big experiments or the part of these experiments that have been running. And this has been known in academia ever since, let's say, 2018 or 19 with this kind of language models. And now it's not just academic research, but it's a reality that we all live together in. But unfortunately, this one is not perfect either. Because at some point, we are not in the position to be able to make the assessment of which answer is correct or which answer is incorrect. For instance, let me actually ask a question. Is that at the very end of my talk, can you actually tell me whether my presentation was scientifically correct or incorrect? It's actually not going to be easy for each one of you to be able to tell precisely that, yes, Professor Joe was like perfectly correct at every aspect, or there were a number of things that were incorrect. And of course, I can always ask you, what were the incorrect parts? It's not going to be easy. So we are actually doing this in a very brute force way at the moment, but it turned out that the brute force way is not that great. And also, it's not just the users who are in this loop, but also the employees of many of these companies that are using these AI systems increasingly more. This is somewhat outdated by now, but unfortunately, this practice hasn't disappeared. For instance, if you are using, let's say, well, I guess no one uses Facebook anymore. Let's say you're using Instagram. Now, obviously, it's not just people like us, but a lot of the malicious users are using Instagram. And then how do we not see them? How do we not see all those porns or the violent materials and whatnot? It's because they are using AI to detect it, but how does the AI system that detects these malicious contents know what are the malicious contents? Because there's tens of thousands, if not hundreds of thousands, employees whose job is to spend 8 hours every day, go through all those malicious contents, and then mark that those are the malicious contents. And then that actually leads to the harms in these employees, obviously. The average tenure of these employees tends to be less than 2 to 3 years, because everyone gets depressed, and then they just cannot work on it anymore. And then, what that means is that at the moment, a lot of the advances or the advanced AI systems that we see are in fact built on top of the sacrifices a lot of the people who did not actually benefit that much from developing these AI systems. So okay, who actually benefited from developing these AI systems? People like me who got really lucky and then timing was good, or the investors who actually invested in these companies, or of course the execs of all those companies who are running these systems. But in fact, the ones who are actually being harmed are the people who are being subjected to, or who are actually providing all those feedback and the signal to them. So this was another example that is kind of somewhat hilarious. Twitter actually claimed that it was not the case, but back many years back, in 2018 or 2019, there was a weird incident where when Twitter showed a preview of a news article that has the picture of, let's say, man or woman or some famous people there, somehow, when it's a man, it's going to put the head and the torso at the center of the picture. But if it's a woman, it would actually zoom in on the breast part of the woman. It's horrifying. Of course, it's difficult to prove it, but there you see, why would this happen? Because thinking about who are actually the people who are providing the annotations and breaking this kind of spurious correlation, because breaking spurious correlation does not mean that we are only getting the correct, let's say, correlations, but the correlations that people who are providing annotations or the developers want. So it turned out that it's not necessarily the best way to go about, because the early deployment, iterative refinement, good only for a very, very toyish and fun applications, but anything beyond can actually result in irreversible damages. And then there are so many examples there is. Even the machine translation system turned out to be fatal in the different parts of the world. And then all those algorithms can actually lead to a very, the incorrect or the harmful, let's say, outcomes depending on what kind of neighborhoods you live in, whether your skin of the color is darker or lighter, and whether you are born a man or woman. So this is problematic, except that this is not moving. I mean, it's a good slide to take a look, by the way, but okay. And then there are so many examples there. I'm happy to talk about it after this as well. And then people have been trying to come up with a way to avoid this kind of thing by incorporating the fact that, okay, the world changes, world has diversity, so we're going to collect the data from different parts of the world, different time, and then try to use the information, the metadata we have, in order to break this spurious correlation that arises from our inability to take into account all those interesting or the different, let's say, metadata. And then we can talk about it, but it's a bit too technical. I'm going to just skip on this part, just saying that it is connected to what people call as a meta learning, which I think is the next, let's say, big step we need to take. But people are trying it. Unfortunately, it doesn't work well. Only thing that has been shown to work well is, again, for us to think a lot and then come up with a way to augment the data, to remove all those spurious correlations. But I just skip this part. So really important thing is that the AI is still in infancy in the sense of making a system that we want, making a system that's going to work in a way that we want it to work. It's very easy to build a system that just works however they want, even if the systems are working in exactly the opposite way that we want them to work. But how do we ensure that the AI system work as we want them to? It turned out that we actually have zero idea at the moment how to do that. Okay, good slide to keep, but okay, maybe next slide. No. Oops. I'm not entirely sure where I should actually point at, but anyway, so say, we don't know how to build it, but of course, this is one thing that it makes me more of an engineer than a scientist, is that the scientists, actually, I'm more of an engineer than a mathematician, because the mathematicians, if they cannot prove something, they tend to get stuck. Scientists, the same thing. If they cannot reject a null hypothesis, they tend to get stuck. But I'm an engineer, so I tell my students, as well as many of my colleagues, that okay, so theoretically, things don't work. So are we going to just sit here until somebody comes up with a better algorithm that is theoretically more sound? No, I'm not going to just sit here. If there are problems that we need to solve, we have to solve it, right? We have to do something about it. That's the reason why all these AI algorithms that have the limitations are deployed and used. And then if you think about it, when we think about building an AI system, we only think about okay, how are we going to collect the data? how are we going to do the training of these systems, and then how are we going to evaluate it? That's the point at which we stopped so far, we have discussed so far, and then we iterate there. However, we have to think about the deployment and the feedback coming from the deployment all the way to data collection procedure as well. And then the reason why we have to think about it are there are two aspects to it. One is the data contamination, and the second is the exploration versus exploitation dilemma. Let's talk about the data contamination. Google Cloud Vision API, you don't have to try it. This is pretty old. Just go to chatgpt.com and then you can actually try it. You just upload the image. You're going to ask what kind of objects are there. It works beautifully, beautifully. That's great. But then, how was this system or that kind of system built, or what kind of data was used? And then one of the main foundation on top of which all the other data set has been built are the ImageNet. And then if you look at the ImageNet, how the ImageNet was constructed, it actually says that it worked with the Google image search. And then Google image search uses this kind of convolutional neural nets that were trained on ImageNet. So there's a weird, let's say, loop that is happening there. So there was the internet, original internet, where everyone was taking pictures, tagging it very, very carefully, writing a captions, and then people are going to leave the comments and so on. Great. And then Google crawled all those things, created a Google image search, and the Google image search initially was using the text that were provided by the users. And then the ImageNet creator team used the Google image search to get the very rough set of the images and then trying to filter them out in order to build a very precise ImageNet that was used initially to train a convolutional neural network in 2012 to get us the first, let's say, commercially, let's say, impactful, let's say, application that is a computer vision, let's say, AI. And then that one became part of the Google Cloud Vision system. And the Google Cloud Vision system is used by users like all of us to automatically generate captions or automatically tag images. And then those things are going to go onto the internet. And Google is going to, again, crawl the internet to increase their, let's say, database for the Google image search, which can be used by the next generation of the image search and the ImageNet. And then this next generation of the ImageNet is going to be used by the researchers as well as developers to build their own image search. And then what you see is that there's something wrong here, right? So what are we actually learning from? Or what are we learning? And then in fact, this is one of the most hilarious examples, is that the Google Translate works really, really well. Nowadays, I would actually go for the ChatGPT over the Google Translate. If you're in Korea, you would use a DeepL or the Naver Papago, but that doesn't really matter. You can replace the Google Translate with whatever the favorite translation engine of yours. So how do people actually build Google Translate in the first place? They crawl the internet like crazy. They crawled the internet, and then based on a little bit of the queue, they found out that many of the web pages are translation of each other for different languages. And they collected it and using the system to build a Google Translate system using so-called AI technologies. But it turned out that we ran into the same vicious cycle. It'll be nice if this one works. Is that when they looked it up already in 2011, and then web pages that are written in Tagalog from the Philippines or Hindi or Galician, half of the web pages were, in fact, the results of the Google Translate already. So using the output from the Google Translate to train the Google Translate is one of the dumbest way to burn GPUs and then burn the forest as well, right? So what they had to do was essentially what they saw was this vicious cycle. So somebody wrote something, let's say one of you wrote some blog post in Korean, and then that goes in, when it's a Google Translate, you got the translated version and you create an English version of that one. And then both of them go into the internet. And then Google is going to crawl the internet to find this so-called parallel corpus, and then trying to use that to improve their Google Translate. And then what you see is that essentially Google Translate is being trained to imitate its own self from the past. And then as you can imagine, that's not the greatest thing to do. So there was a vicious cycle. So how do we actually then break this vicious cycle? There are some algorithmic solutions that dates all the way back to 2011 or even before that is called the statistical watermarking. So we can alter the output just a little so that statistically later we can detect whether a particular web page was created by the Google Translate or not. We can always do that. Unfortunately, doing so results in the trade-off between recall and quality, or in this particular case, the recall and translation quality, and then this applies to everything. And nowadays, you do see all those images generated from the DALL-E 2 or nowadays Grok 2 and all those different models. And then sometimes you actually have a trouble detecting whether that was generated or not. And then the people want to come up with this kind of watermarking technology, but the technology will always result in some kind of degradation in terms of the quality. Now, how do we actually minimize that is one question. And then second is that how do we actually ensure that the degradation is not going to disproportionately affect the particular type of the applications or particular type of the geographical, let's say, regions as well. And then the funny thing is that this kind of statistical watermarking seems to be great in this kind of Gen AI era where everyone can create this kind of misinformation, disinformation, fake images, and so on. But we have to be a bit careful there because this also means that the people can always use this kind of technology to track where the data is flowing and then from whom to whom. And then all those things can be used for the evading the privacy as well as for the better manipulation than before. So what is the right way to, let's say, make this perfect trade-off is going to be an ongoing discussion we need to have at the society level as well. Now, unfortunately, this problem is getting worse every day rather than less lessened. And then we have to think about it very carefully. And I heard that there are some of the very horrifying instances that have happened in Korea about the deepfake and so on. Now, so can this, in fact, this really urges us as a society to think about it really, really seriously at this point. So finally, I want to do a bit of a social experiments here. So you're probably here with your friends or whoever is sitting next to you is fine. If you open your smartphone or your laptop, you can go to say naver.com. If you're using Naver, you can go to news.google.com, and then look at the top 5 news articles. And then trying to compare the top 5 news article with the top 5 news article of the people who are sitting next to you. What you're going to see is that in particular, if you're looking at it from the service that you use, then you're going to see that they are all different. They're all different from each other. And then that is actually a really interesting observation. What that means is that the type of the information as well as the amount of information your friend consumes is significantly different from the information that you consume yourself. And then that's true for almost everyone that you can find. And then what that also means is that there is something going on here. It's not the same thing that everyone is seeing. It's not the same aspect. Even the same event is going to be covered differently across by the different journalists and different newspapers. And then you get to see one aspect while your friends get to see other aspects. And then this is a personalization of this kind of news articles. And the personalization on its own is not a bad thing. In fact, I would even say that it's a necessary thing, in particular these days when we are completely flooded with the information, whether they are correct or or the disinformation. So it is necessary, but how does this personalization work and what is the right way to do it? And then here comes the question of the exploration versus exploitation. It's impossibly simple insight that turned out to be extremely important for building this kind of AI systems is that unless you tried it out, you will never know whether you like it or not. If you haven't watched movies from, let's say, India at all, how would you know that you like it or not? And then that part implies that you need to explore a bit in order to tell what is the things that you're going to like. And then once you know about your own preferences, then you want to go deeper and deeper into following your preferences. And all these algorithms are doing that. And any good recommendation algorithm has to explore alternatives that is by the exploration. And we can talk about the algorithmic details, but I'm going to skip through. But this is the idea of the so-called bandits or the reinforcement learning. And that is that the exploration is necessary. And then this actually connects to one of the most important principles in reinforcement learning called optimism in the face of uncertainty. If you don't know, because the future is uncertain, we have to be optimistic in order to try out the various solutions that are going to lead us to a better outcome. Now, unfortunate thing is that there is a dilemma, is that this can be manipulated very easily, and also exploration cannot often catch up. And that is that most of the companies have the incentive that are aligned more with the exploitation rather than exploration. Is that instead of showing the users all those random things that they may like, but wouldn't you want to actually mix in a bit of a signals that are going to align better with the advertising revenues and whatnot? So there is a dilemma that is happening because it turned out it's not only about the exploration and exploitation, it's exploration, exploitation, and revenue making as well. And it turned out that a lot of these companies, and then since some of you are startup founders, you're very tempted to do that, have been running and continue to run this kind of massive scale A/B testing. Facebook has been running this kind of testing a lot. All the other major companies that you can imagine have been running this. And then that actually allows them to learn about each and every one of you, including myself, extremely, extremely well. And then sometimes it is very tempting for these service companies as well as your own startups to run experiments that we probably shouldn't run. In fact, this is a paper, it was an extremely controversial paper from 2014 where the team at Facebook ran an experiment, massive A/B testing, to test whether showing more emotionally charged posts to the users would make those users come back more often and spend more time on their platform. And then you can now see where it's leading to. If the emotionally charged posts do bring users come back and they engage longer, you probably want to show them more emotionally engaged posts. And then what are those emotionally engaging posts? Often the polarizing posts. So you can imagine how other kind of malicious companies or the actors can run this kind of experiments. And then we have to be all very aware of this potential, this kind of, unfortunate potential, which is kind of, necessary as well. As we talk about it again, exploration, exploitation, necessary component to build a good AI-based recommendation systems. And then there are, of course, the ethical concerns there, but I'm going to skip that part for a second if it works. So, and then why is it actually not easy for us to simply build an AI system, claim that it works, and then deploy it? Because there are cases where we really shouldn't do unless we are 100% sure, because there will be truly irreversible damages. So hiring, this was a very insightful as well as a sad story from the 2019. Oh, actually, I think this is from 2018 or so. So Amazon is a massive company. If I recall correctly, they have 1 million employees at the moment in US. And then, of course, they receive probably tens of millions of the CVs every year or every month. So how do you actually go through all of them? So they decided to actually deploy the AI system that's going to read the CV and then make kind of, all-lead determination whether or not they're going to exclude them or not. And then initially they realized that, in the initial testing, okay, this is not good for the engineering positions as well as the business positions. This system is effectively just ruling out all the women. Not a great idea, because if the word is actually half woman, and then if you are losing out on the half of the people, that doesn't make any sense. So they decided that okay, so we're going to make these systems blind to some of the phrases that suggest that this applicant is woman. Let's say women's college, or the woman make it blinded. And then the list of the colleges that are known to be women's universities or colleges, make it blind. Turned out, okay, of course, as you can imagine, making them blind doesn't change it, because from the context you can infer those things. And then they were running this kind of secret kind of AI recruiting tool for a few months or a few years, and then they decided to shut it down. And then what this actually tells us is that during that period, all those people, especially the women who applied to AWS or the Amazon, were secretly disadvantaged by this AI algorithm that they didn't know that were, putting women in the disadvantaged positions. And then these kind of things cannot be reversed. Those people lost those opportunities during that 1 year, which is a massive, in particular, if you think about when is the most actively, job-seeking period. That's the 20s. And you take the 1 year out of it, that's really bad, right? So AI in deployment can and will introduce some kind of vicious cycle. There's a high chance of doing so. So we have to really think about it, not as a static system that you're built and then say that, okay, this system now works, let's deploy it. But it's all about how to continuously evaluate, assess, and then adapt the system to the changing environments, because this kind of system, when it's mass deployed, is going to change the society directly as well. So how do we actually ensure that this cycle remains virtuous? That's the major question every developer, every founder, as well as every user, and then people who are actually being subjected to use, because the applicants to Amazon did not even know that they were being subjected to this kind of AI system. So we all must have to think about it very, very carefully. So to just conclude it, One of the most important things is that if you're building a system that depends on some kind of data, you really have to know what kind of data that is. We all want to, no one wants to take responsibility or be accountable down the road, and then we tend to want to push that kind of responsibility down the road. We want to say that, well, we were just using API. We didn't know that the OpenAI was going to change the model. We just used this Naver API. We were using this model we downloaded from the Hugging Face Model Hub, and then we didn't know what kind of data they use. Yes, you can say that, but that's a lazy way to deflect the responsibility that you actually have made, because it's not like you're actually not going to make money out of it either. So it's really important to know what kind of data you're using. And then also it's really important for you to know what kind of model you're using. At the end of the day, all these models are essentially the different transformation of the data. So even if you know the data, if you don't know the model, then you actually don't know what kind of system you're building. And then again, you might want to actually just pass on the responsibility to the others, but we are not supposed to do that. And then the most important thing is this kind of imagining the future consequences, the value misalignment problem. Instagram is I'm a huge Instagram user. I love it. I use Twitter as well. I use all those things. And then I try to imagine what they had in their mind when they created the Instagram. What happens? Who are the people who are happy? People who have a lot of friends, who hang out with these friends. They're having fun. Those are the happy people. So that seems to indicate that, okay, more engagement that people have, they tend to be happier. So then we're going to make a platform that's going to maximize the engagement by the users, thereby make the users all happy. But as we see these days, Instagram users, in particular the young women, like in teenage years, are the way less happy than they were before because of this kind of filter effect. Is that they see all those friends who are going to this amazing vacation, and then you're eating amazing things, hanging out with these amazing people, unlike me, and then everyone gets unhappy. And then this kind of, let's say, misalignment of the values that everyone has is something that we cannot really fix because everyone has their own value. We don't want to impose anyone's value on the users or anybody else, but being able to imagine these differences across the values must be something that we have to keep in our mind, again, as a developer, entrepreneur, user, as well as the people who are being subjected to this kind of technologies. So this is 5 recommendations I found from the position paper titled "The Ethical Machine Learning in Healthcare" by Irene Chen and others from 2020. Now, it's about healthcare. Healthcare is a very mission-critical domain, so all of this may not look like they are going to apply to here, but because AI is used everywhere, we should take this kind of, strict, guidelines or the recommendations that were made by the channel and then trying to keep that in our mind. So we have to really make sure that we have a diverse set of teams that are going to reflect the user groups as well as essentially the entire society as close as possible so that we can increase the probability that the equity will be achieved. Second is that we have to ensure that the data collection, so what kind of data we're going to collect and how that data is going to be used, has to be at the front of the mind. And then third is that we have to be really careful about how we measure and then what kind of outcome we are going to measure as an objective. It turned out user engagement was a horrible objective because everyone became unhappy eventually. So what is the real outcome that we want to maximize or measure in order to make sure that our AI systems are going to be beneficial to everyone? The fourth one is going to be that we have to think about those outcomes or the goals from the very beginning. We cannot simply say that, oh, I want to make a smile detector so that my those robot docents are going to blink whenever the user smiles. But what was the goal of doing so? We just built it, trying to sell it. That's not the goal. Goal is what we want to achieve, and then that has to be at the very, very beginning. And finally, this is really important, is that we have to have a way to audit the systems. This may be done by the developers themselves, or this preferably done by the third-party vendors who can actually audit the potential harms that are going to be induced by these systems so that we know. And then a lot of software engineers actually kind of oppose to this idea, oh, how do we audit what's going to happen in the future? However, in many of the fields in the current society that are extremely, let's say, competitive as well as fragile and also potentially dangerous, such as finance sectors, healthcare sectors, drug discovery, all these actually sectors do require the various auditing because we know that the missing out on some of the potential harms can wreak havoc on the society. So we should be able to come up with a way to audit this kind of algorithms or the AI systems as well. Not sure what to do about it, but there are a lot of people who are working on that at the moment in various universities. Actually, I'll just skip this part because I was making fun of too many people. I'll skip this, but you'll see that what is the issue there. And then this actually concludes my talk. I don't know how long, I'm probably way over time, but if there are any kind of, let's say, things that you want to discuss, I'll be around for another 10 or 20 minutes after the talk. Thank you very much.